Imaginary and complex numbers. So basically mathematicians got stuck on taking square root of negative numbers, so they came up with an imaginary number, I. And this is how they deal with taking the square root of a negative number. So they let I equal the square root of negative 1. Alright, so no matter what we do with these, I can always break down the negative 1 and pull it out. So square root of negative 16 is just the same thing as the square root of negative 1 times 16, which is the square root of negative 1 times the square root of 16, because those break apart. So being that this equals the I, because the square root of negative 1 equals I, that's just I times 4, or 4I. Okay? So a couple other examples. If I did the square root of negative 81, honestly, the way I like to think about it is I pull the negative out as the letter I, and then the square root of 81 is 9. So it's just 9I. But that's all the math broken down. Alright, again, we've got the square root of negative 45. So I take the negative out by writing the letter I, and then I use my calculator to figure out what the square root of 45 is. Honestly, it's the square root of 9 times the square root of 5, and then the square root of 9 is 3, so you pull out the 3. So you can break it all down, but use your calculator. So when I pull this out, I get 3i square roots of 5. So the I is usually written between the number and the radical. So if you write it, that's where it goes. Alright. Now, this letter I is an interesting little character because as you raise it to different powers, okay, it has different values. Because if you take the square root of negative 1 times the square root of negative 1, the square roots go away, leaving you with just negative 1. So here's what happens when you're raising I to a power, and yes, 1, 2, 3, 4 are your bases, alright, and then after that you just have to divide by 4, and I'll show you what I mean. But I to the first is obviously just I, okay? I squared is negative 1. I cubed is negative I, because I took that negative 1 and multiplied it times I, because 2 plus 1 is 3, okay? And then I to the fourth is positive 1, because that's I squared times I squared, so negative 1 times negative 1 is positive 1. Alright, so the way I try to remember this, if I can write I to the 1, 2, 3, and 4, and then I1, negatives in the middle. Okay? I1, negatives in the middle. That's how I remember the list. Okay? So now you can use that to figure out any value for I that's raised to an exponent by dividing that exponent by 4. So if you think about it, if I divided a number by 4 and I got 0.25, that's 1 over 4, right? So it would be I. If I got a remainder of 0.5, that's 2 over 4, it would be negative 1. If I got 0.75, it's negative I. And if I got 0.0, or it goes into it evenly, it's positive 1. So let's look at some examples. I to the 13th power. I'm going to put 13 over 4 into my calculator. I get 3.25. 25 goes with I. So I to the 13th power simplifies to I. Alright, I to the 27th power, 27 divided by 4. I plug that into the calculator and I get 6.75 when I make it into a decimal. And then, so I go to my 0.75 equals negative I. So I to the 27th power simplifies down to negative I. 54 over 4 gives me 13.5. 0.5 is up here at negative 1. So I to the 54th power just equals negative 1. I to the 72nd power, 72 divided by 4 goes in evenly 18.0 times. So my 0 went with 1. So I to the 72nd power just equals the number 1. Alright, then we have complex numbers. Complex numbers are taking a real number and adding it to an imaginary number. So it's that binomial that's created. So you get this a plus or minus bi. Alright, so some examples of complex numbers were 2 plus 3i, negative 7 minus 2i. I could have negative 7 plus 3i. I mean, it's just a real number and an imaginary number stuck together with an addition or a subtraction sign. So you can graph them by treating them just like they're an ordered pair. So I'm going to put my real axis as my x-axis, my imaginary axis is my y-axis. So a plus bi, this is how far I move left or right, depending on if it's positive or negative, and this number is how far I move up or down. So if you look at these points, this is the point 4, negative 3. So 4, negative 3i is how that's graphed. So this is graphing on the imaginary grid. Alright, to add and subtract complex numbers, you treat the i's just like they're variables. You combine like terms where you can. You always combine real with real and imaginary with imaginary. To simplify, you've got to have no powers higher than 1. So I squared, I to the 4th, I to the 13th, whatever you get, you've got to simplify that down. And then you write the answer in standard form, meaning the real part comes first, the imaginary part comes second. So some examples. And this comes from the worksheet that you were given in class to watch the video. So some examples, we've got the 3 plus 2i and 7 plus 6i. So 3 plus 7 is 10, 2 plus 6 is 8, that's it. Okay, then we've got our 6 minus 5i minus 1 plus 2i. Got to distribute that negative to both pieces just like it were a binomial. And so I get 5 minus 7i because 6 minus 1 is 5, negative 5 minus 2 is negative 7. Alright, then I've got the 9 minus 4i minus negative 2 plus 3i. Distribute the negative. When I do that, it makes the 2 positive, it makes the 3 negative. Combine my like terms. When you have something like this that looks a little longer, or we've got like complex number shoved right in the middle of a complex number, you just distribute the negative and combine like terms. So it's 9 minus 10 minus 2i minus 5i. So it's just negative 1 minus 7i. And for these two, I went ahead and distributed the negative first, and then I dealt with all of these numbers. So 4 over 4 is 0, which meant that simplifies to 1. 3 over 4 is 0.75, which means that simplifies to negative I. 4 over 4 goes back to 1. 3 over 4 goes back to negative I. And then, so what that means is I've got 11 times 1 is just 11. Positive 4 times negative I is just negative 4i. 2 times 1 is 2. Negative 2 times 1 is negative 2. And then positive 6 times negative I becomes negative 6i. And this combine your terms. When you're multiplying them, it's almost the same. You still treat the I like variables. Change all the i's that are not in the first power. So I know this seems like a lot of notes, but I'm going through them because this is not a lot different than polynomials. So you treat them just like they're polynomials, except at the end, if you end up with an I squared, you got to change it to negative 1. So here's some examples. We got negative I times 3 plus I. I multiply the i's in. Negative I times I is negative I squared. Okay? I squared is the same thing as negative 1. A negative minus a negative is just a positive. And then you just got to rewrite it with your number first and your imaginary part second. These four here are just like what we were doing with the distribution with the binomials. So we've got the 2 times negative 6 is negative 12. 3 times negative 2, or excuse me, 2 times negative 6 is negative 12. 2 times negative 2i is negative 4i. 3 times negative 6 is negative 18i. Positive 3 times negative 2 is negative 6i squared. So the very first thing, or the two things that I do is I move from here to here, or I combined my like terms, and I got the 22i, and I replaced I squared with negative 1. Okay? Then I went ahead and multiplied those through and combined my terms. For this next one, I multiplied the 3 times the 8 for negative 24, 3 times negative 5 for positive 15i. Then I multiplied the i's through for the 8i and the negative 5i squared. Combine my like terms at the same time that I changed the I squared to negative 1. And then we have our answer when we combine all of our like terms. And then you can see what I did for those two steps. There was one more on that page, which is right here. Okay, so you don't really divide complex numbers, but complex numbers are not allowed in denominators. So when imaginary and complex numbers end up in the denominator, you have to rationalize the fraction. So all that basically means is that we're going to multiply the top and bottom by the conjugate of the bottom. So a conjugate is what we use to do this. And a conjugate is just the exact same complex number, except the middle sign is changed. So the front sign is not changed. It's not change all signs. It's just change the middle sign. So we've got the conjugate to 2 plus 4i is 2 minus 4i. The conjugate to negative 3 minus 7i is negative 3 plus 7i. So I only changed the middle sign. So to rationalize a fraction, you multiply the top and bottom by the conjugate of the bottom. So I'm not multiplying the bottom times the conjugate and the top times its conjugate. They're both being multiplied by the same thing because anything over itself just equals 1. So when I multiply these through, I multiply just like I was doing above, and I end up with 31 minus 46i. When I multiply the bottom, the 3 multiplied times the 3 is 9, and then I got 3 times negative 8 is negative 24. 8 times 3 is positive 24. And then the 8's multiply together to give me negative 64i. Well, these two guys cancel out to 0. This is just the same as negative 1, so it becomes positive 64. So 9 plus 64 equals 73. So it completely gets rid of the complex number on the bottom. So if we take a look at the couple different examples from your worksheet, I've got my negative 1 minus 2i, so I change those to positives in the middle, and then I multiply straight across. So I multiply 3 plus 11i times negative 1 plus 2i as if they were binomials. When I did that, I ended up with I squared at the bottom, so I changed that to negative 1 and made that negative 22 before I combined all my like terms, just like I did down here, and it ends up being 5. Now if I take a look, I got negative 25 minus 5 over 5. That's a whole lot of 5s. Since 5 can go into both pieces, I simplify that. So my answer is right here at negative 5 minus I. They won't all simplify, but if they can, you want to. Same thing here. I multiply the top and bottom by 1 minus I. Now I'm kind of lucky at the top here. I don't have a whole complex number. It's just a real number. So I just distribute that into the top, work on multiplying the complex numbers at the bottom like they're binomials, and I end up with 2 after I combine all my like terms. Then I've got 8 plus 3i times 1 plus 2i, because I've got to change this to 1 plus 2 to be my conjugate. Now I've got to multiply these like binomials. I cross out my I squared, change that to negative 1, and I multiply negative 1 times positive 6 before I combine the terms to get 2. Combine those terms to get 19i, and then what we get here is basically 1 squared plus 2 squared, so that's going to be 1 plus 4 is 5. The next two you end up having to simplify, so then what's nice about these is that it's not a complex number, it's just an imaginary number. So you don't have to worry about signs at all, you just multiply the top and bottom times the imaginary number. So I distribute the 2i into the top and I get 12i minus 6i squared, change that to a negative 1, so it's negative 6 and negative 1 is positive 6, 12i, and then 2 times 2 is 4, I times I is I squared, that makes it a negative 4. All even numbers here so you can simplify. So negative 4 into 6 is just 3 halves. Negative 4 into 12 is just negative 3. Here's the same thing, just because it's a complex number, it's not a complex number, I can just multiply the top and bottom by 3i. So 15i plus 18i squared over, and this ends up being negative 9. 3 times 3 is 9 times the negative 1 you'd get there. So I get 9 under 18 and 9 under 15. All those numbers can be divided by 3. So 9 goes into 18 2 times. They're both negative, making it positive. 9 under 15, it goes in 5/3, and then you bring your I down and keep it next to it.